There is a direction to the two words necessary and sufficient that you have to understand in order to understand the math mnemonic TONCAS, or TONCAS. There's no way to say it that doesn't sound goofy. I'm just going to say TONCAS. Necessary goes in this direction, and sufficient goes the other way. If you've learned about mathematical proofs, then you know what I mean by these two words having opposite directions. But if not, let me explain. In the case of necessity, for example, it's necessary to eat in order to live. Since it's necessary to eat in order to live, if you are alive, that means that you must eat. And as for the word sufficient, if it's raining, that is sufficient for the ground to be wet. Since it raining outside is sufficient for the ground to be wet, if it is raining, that means the ground is wet. You can see that necessity goes one way and sufficiency goes the other. Eating is necessary to live, but it's not the only thing. It's not sufficient. So if you eat, it's not necessarily the case that you will live. You also need water, you need shelter, you need many things. On the other hand, while rain is sufficient for the ground to get wet, it's not necessary. If the ground is wet, that doesn't imply that it's raining or has rained recently. The ground could be wet because of puddles from rain from the previous day. The ground could be wet because somebody spilled a water bottle. There's many different reasons. It's not necessary for it to rain for the ground to get wet. When something is necessary and sufficient for some other thing, we say that they are equivalent. For example, to not be marked tardy, it's certainly necessary that you show up to class on time. On the other hand, if you show up to class on time, in fact, that is sufficient to not be marked tardy. These two things are equivalent. Showing up to class on time is what it takes to not be marked tardy, and vice versa. Certainly, in mathematics, this distinction between necessity and sufficiency is very important. For example, in order to be a prime number, greater than or equal to 10, it's certainly necessary that the number is odd. Otherwise, it will have 2 as a factor. 10 isn't prime, 12 isn't prime, 14, 16, not prime. They're not odd. While it is necessary to be odd, it's not sufficient. 11 is odd and prime, 13 is odd and prime, 15 is odd, but it's not prime. In this case, although it's obvious that for a number that's greater than or equal to 10 to be prime, it certainly has to be odd, that is not sufficient. But sometimes the obvious necessary condition is sufficient. That's TONCAS. TONCAS is an acronym meaning the obvious necessary condition or conditions are also sufficient. The reason this mnemonic came to be in the first place is because, particularly in the field of graph theory, we find that it's often the case that the obvious necessary condition is also sufficient, which generally speaking is pretty surprising, but in graph theory it happens a lot. So I want to show you 3 examples in graph theory, you'll get a nice little introduction if you need it, that the obvious necessary conditions are also sufficient in a few different problems. A graph is a structure consisting of nodes and edges. Each edge joins a pair of nodes, so this is an example of a graph here. One question we might ask is if it's possible to color the vertices of a graph so that no 2 adjacent vertices are colored the same. So no 2 vertices that are joined by an edge should have the same color. Is it possible to do that with this graph? Well, if we try, we might color this vertex blue, then this vertex can't be blue because it's adjacent to this blue one, and this vertex can't be blue either because it's adjacent to that blue one. But there's nothing stopping us from coloring that vertex blue, which forces us to not color this one blue. So can we color the rest of the vertices with just a single color? Yes, we can, because none of them are adjacent. We can color this one red, and it's only adjacent to blues. We can color this one red, it's only adjacent to blues, and we can color this one red, it's only adjacent to blues. So in this case, it is possible. When a graph can be colored this way, it's called a bipartite graph. We've split the graph into these two parts, in this case, the blue parts and the red parts. And so early graph theorists asked this question: when is a graph bipartite? When is it possible to color the vertices of a graph like this with just two colors, so no two vertices of the same color are adjacent? Of course, if you were trying to answer this question, you would start by investigating some simple graphs. Here's another one. This is called a triangle graph or a cycle graph on three vertices. With this graph, we encounter a problem. If we try to color this vertex blue, then we see these two vertices cannot be colored blue, so they will both be forced to have whatever the other color is. Let's again say that it's red. They're both forced to be red because they're adjacent to this blue vertex. But of course, they're adjacent to each other, so we're forced to have these two adjacent vertices that have the same color. We thus see that it's impossible to color the vertices of this graph so that no two vertices of the same color are adjacent. This graph is not bipartite. Again, it's a cycle graph on three vertices. And you will encounter this same exact problem if you try to color the vertices of any odd cycle. 3 is odd, and we had that problem with this graph. 5 is another odd number, so this is another odd cycle, and it gives us the same issue. If we tried to color the vertices of this graph, we could color this one blue, then these two can't be blue, but then this one can be blue, and then we could go try to color it the rest of the way. This vertex is forced to be red, this one's adjacent to blue, so it's forced to be red, but then this vertex is adjacent to both red and blue, so there's just no possible way to finish this coloring. This odd cycle is not bipartite. So graph theorists reasoned, obviously, it's necessary that a graph doesn't have an odd cycle for it to be bipartite. But in this case, it turns out that TONCAS is true. The obvious necessary condition is also sufficient. So we would say that a graph is bipartite if and only if it has no odd cycles. I know two things from this statement. One, if a graph is bipartite, it must not have any odd cycles, because I know that's necessary. But furthermore, if a graph has no odd cycles, then I immediately know it's bipartite, because not only is it necessary to have no odd cycles, it's also sufficient. And note what I mean by having an odd cycle. This graph is an odd cycle, but if it had some more stuff going on, like an additional edge, some more vertices, this graph isn't an odd cycle anymore. It's more than that, but it does have an odd cycle, so it's still certainly not bipartite. One of the things you'll find if you study graph theory is that the obvious necessary condition is usually easy to prove, but to prove that it's also sufficient is often much more difficult. So we're not going to prove this, and we're not going to prove the next claim either, but we will give a justification of the last example. Moving on to our second example, which is also very famous. One of the important things to know about graphs is that although they're very nice to draw, it doesn't matter how you draw them. The way we draw a graph does not affect its structure. So while this graph looks curvy and wacky, it is exactly the same as this graph here. You can see that they're both just paths between four vertices. Although we may consider a graph typically to be defined completely by its structure and not how it's drawn on a piece of paper, there are some times where we do like to consider the drawings of graphs and how they're embedded in the plane, as we say. For example, I have 4 vertices here, and what I'm going to try to do is join every pair of vertices by an edge. That's called a complete graph. So every edge that could exist, I want to put it in this graph. My objective is to draw those edges so that none of them intersect. Or if you view these two edges as intersecting at this vertex, then stated differently, I want to draw all the edges so that they only intersect at the vertices. If you try to do this yourself, you might come up with a different solution. There are many ways to do it, but this is one cute way to draw the complete graph on 4 vertices so that none of the edges intersect except at the vertices. This is called a planar embedding of the graph, and so naturally graph theorists asked, when does a graph have a planar embedding? When can it be drawn in the plane with no edge crossings? Again, graph theorists investigated this problem and tried to figure out when it was and was not possible to embed a graph in the plane. And it doesn't take long to find a simple example that just doesn't seem possible. Here are 5 vertices. I invite you to pause the video and try yourself to draw the complete graph on 5 vertices, so every possible edge, without any edge crossings. We could start to draw in these edges however we like, just trying to avoid any forced crossings of the edges. It doesn't take long for the diagram to start getting a little bit cluttered. At this point, the only edge I have left to draw is between these 2 vertices, and at least in this case, there's just no way to do that. Now, maybe if I drew it differently, it would be possible, but I can confirm for you that in fact, it is not possible. Further investigation turned up another example of a troublesome graph where it just didn't seem possible to find a planar embedding. This is the graph famous from the 3 houses and 3 utilities problem. The idea is that we have 3 houses, 3 utilities, and we're trying to connect all utilities to all houses without any of the connections intersecting. Again, you can give it a try yourself. You're not going to have much luck. Initially, as we start to connect utilities and houses, everything seems to be going hunky-dory, but again, we'll quickly get into a big fat mess that we just can't get out of. I can sneak in a connection here from this house to this utility, and I can connect this utility to this house, but there's just no way to get this last connection without a crossing. And so again, graph theorists reasoned, obviously it's necessary that a graph doesn't have this structure, which is called K33, and doesn't have this structure, the complete graph on 5 vertices, called K5, for it to have a planar embedding. It's necessary that it doesn't have these structures. But once more, with a slight adjustment, it turns out that we have TONCAS. The necessary, or I should say obvious, necessary conditions are once again sufficient. Here's the slight generalization that needs to be made. Obviously, if a graph has this structure, you're not going to be able to make a planar embedding of the graph because this structure does not have a planar embedding. But imagine we take any edge, like this one for example, and subdivide it into 2 edges by adding an additional vertex on the edge in a way. So we've turned that one edge into 2 edges that deal with this new vertex we've just added to the graph. At this point, this is a different structure. I mean, it has a different number of vertices. It has a different number of edges. It is a different structure. In fact, this is called a subdivision of K33 because we took one of the edges and subdivided it. And we could do that on other edges as well. So we've just taken that edge and turned it into 2 edges that work with this new vertex. And we could do that repeatedly over and over again to as many edges as we like. Although a subdivision of K33 is not K33, it too will fail to have a planar embedding, and that's the generalization we need to account for to have TONCAS. I should also finish the job here and actually make this K33 by drawing that edge crossing. So the TONCAS theorem in this case is that a graph is planar if and only if it doesn't contain a subdivision of K5 or K33. This theorem is considerably more difficult to prove than the previous one, though once again, it's the sufficiency part of this theorem that's far more difficult to prove than the necessity part. One direction is hard, the other direction is pretty easy. Alright, one more example where we'll actually go through a quick argument to justify the theorem. Let me just sketch out an example of a graph here. Let's say this is our graph. Note that it has this, what we call isolated vertex, that's not adjacent to anything. That's fine. It's just part of this graph. It's a vertex all by itself. No problem there. There's something in graph theory called the degree of a vertex, and I'm going to label the degrees of these vertices in blue. The degree of a vertex is the number of edges incident to the vertex. The number of times an edge touches a vertex, that's its degree. So for example, this vertex is not touching any edges, so its degree is 0. An edge touches this vertex once, so its degree is 1. An edge touches this vertex twice, so its degree is 2. the degree of this vertex is 3, and the degree of these two vertices, both 2. Then, the degrees of every graph can be used to write its degree sequence, which is just the sequence of its degrees traditionally written from greatest to least. So in this case, the degree sequence is 3, 2, 2, 2, 1, 0. That's the degree sequence. Here's a quick question. If we represent the degree of an arbitrary vertex as di with this graph, what's the sum of all of the vertex degrees? Well, we could just add up the terms in the sequence. That would be 3, 5, 7, 9, 10, plus 0 is 10. So the sum of the degrees is 10, which is an even number. That should make sense because every edge is touching two vertices, and thus every edge will contribute 2 to the sum of the degrees. So when you add up the degrees of the vertices of a graph, you'll always get an even number. Certainly, every graph has a degree sequence of non-negative integers, but it can't be the case that every non-negative sequence of integers could represent the degrees of the vertices of some graph. So when is this the case? Well, obviously, for a sequence of non-negative integers to represent the degrees of some graph, the sum of all of the numbers must be even. So if that obvious necessary condition is also sufficient, then a sequence like this should have a corresponding graph whose vertices have these degrees, because this is a sequence of non-negative integers, and the sum of the numbers is even, so this should work. Though you may quickly find that it doesn't work. My first vertex needs to have degree 2, which means that it needs to be adjacent to the other two vertices in the graph, but those two vertices need to have degree 0, which means they can't be adjacent to anything. This just does not seem to work. But once again, if we permit a small generalization, everything works out fine, and we'll once again have TONCAS. There are kind of two rules here that we haven't said but have just been following, which is that 1, an edge can't join a vertex to itself, and 2, we can't have multiple edges between vertices. So we can't have something like this, an edge joining a vertex to itself, and we can't have something like this, multiple edges between the same pair. It is very common that these things are not allowed, and when we don't allow them, that's called a simple graph. However, if we choose to permit loops between a single vertex and multiple edges between pairs of vertices, thus considering what are sometimes called pseudographs, then we will have TONCAS. The obvious necessary conditions will be sufficient. So if we allow pseudographs, then indeed, any sequence of non-negative integers will represent the vertex degrees of some graph as long as the sum of the integers is even. For simple graphs, a sequence like 2, 0, 0 causes problems, but in pseudographs, there's no problem at all. This single vertex can be made to have degree 2 by drawing a loop on itself that is considered to have degree 2. There are 2 times that the edge contacts the vertex. And then we just have 2 isolated vertices, which both have degree 0. And thus, this graph has this degree sequence. Here's another example of a sequence of non-negative integers, and I'll briefly walk you through the general argument that you could use to prove there will always be a graph with this degree sequence as long as the sum of the integers is even. In this case, of course, it is even. We see it's 3, 6, 8, 9, 10. First, you have to understand that if the sum of the integers is even, then there must be an even number of odd terms in the sequence. If we had an odd number of odd terms, then the sum couldn't possibly be even. So it's going to be guaranteed we have an even number of odd terms, which means we'll have an even number of odd degree vertices. So take that even number of odd degree vertices. In this case, we have 4 odd degree vertices, and arbitrarily pair them. For example, pair these 2 and these 2. Join them with an edge. Since these are the vertices that have to have an odd degree, by putting one edge on each of these vertices, there will be an even amount of degree left that we need to account for. For example, this might be the vertex that has degree 3. We've just accounted for one of the 3 edge touchings. We need to add an even number more. Let's say this vertex also is supposed to have degree 3. We've just accounted for one of the edge touchings. We need 2 more. We need an even amount in addition to this. Of course, if these 2 vertices are those that are supposed to have degree 1, then they're all done. They don't need anything else. But for those odd degree vertices that need an even amount of additional edge touchings, you can satisfy that by just adding an arbitrary number of loops. In this case, each of these vertices needs 1 loop. That will contribute an additional 2 to their degrees. Now both of these vertices have degree 3. So we've just fully dealt with the vertices that have odd degree. For all the vertices that have even degree, we can account for that by just using loops, because each loop will contribute 2, an even number to the degree, and you can just do that repeatedly to get whatever even degree you need. If we need an even degree of 2 with this one additional vertex, just draw 1 loop. Now its degree is 2. If we needed its degree to be 6, we would draw 3 loops on it. In this way, we're able to basically pick its degree without affecting the other vertices. Although this might feel like a pretty contrived construction, it works perfectly and is sufficient to show this works. This exact technique can be applied to any sequence of non-negative integers that has an even sum. So that's a bit about TONCAS, a graph theorist's favorite math mnemonic, and some of the basic examples that led to this mnemonic coming into existence in the first place. Like I said, from everything I can find, this is mostly particular to graph theory, this phenomenon of the obvious necessary condition often being sufficient as well. So let me know what you think about that, and if you have any questions down in the comments, and be sure to subscribe for more of the swankiest math videos on the internet.
Free from my fate, twisting to escape this. Climbing out of my wrist if you can break it. Breaking in my past, I'm making it up fast. So slow down, give me the time so I can fake it. Erase the tune of words and just how I say shit. And let me speak my poetry to your face. It's not in the mid if you ain't listening. Not infinite if you ain't really in it.